Dear listener, welcome to my channel. This is fourth video on pause tagging. In this video, I am going to solve pause tagging using hidden Markov model, that is HMM Viterbi algorithm. Let us start. Hidden Markov model for the pause tagging comes under the category of generative model. In generative model, the flow is downward side, that is class generates the data, and comes under the category of probabilistic model. In my all previous videos of pause tagging, I already explained how the hidden Markov model is formulated, or the particular formula for the hidden Markov model. So for hidden Markov model, we are multiplying the two formulas. One is bigram and one is the Bayes rule. Now in this diagram, this POS is nothing but the part of speech tag of previous word, and this is the part of speech tag of current word, and this is the current word. Now we have to determine part of speech tag of the current word. To determine the part of speech tag of the current word, we require the previous tag and this current word. So this is nothing but the state transition probability. For example, Q1 and Q2. So Q1 is previous state, Q2 is current state. We know the part of speech tag of the previous word because we already determined by using HMM model, and here the word is given, and based on this probability, so now Q1 and Q2, they are nothing but state transition probability, and this from this particular part of speech tag class this word gets generated, so this is called emission probability. Now here state transition probability we are using with the diagram, and for the emission probability we are using the Bayes rule. Now formula is probability of part of speech tag 2, which we have to determine, is given the current word, that is the word, and the previous part of speech tag, is equal to probability of word given pause 2 into probability of pause 2 given pause 1. To understand this video, you have to understand the detail of Bayes rule and diagram of HMM model. Bayes rule data obtained from emission probability matrix, while diagram data is obtained from the state transition matrix. Emission probability matrix: from a given corpus, identify unique tokens, also identify total part of speech tag present in corpus. When we solve the example, at that time all the points of the emission probability matrix and state transition probability matrix will get cleared. Assign correct part of speech tag for every token. Arrange tokens in horizontal and part of speech tag in vertical fashion. We can change this order also. This will provide the data for Bayes rule emission probability. For n tokens, m part of speech tag, size of the emission matrix will be n into m. After the formation of the emission probability matrix, we form the state transition probability matrix. Use part of speech tag found from the emission probability matrix. Create a matrix size of m into m, where m is nothing but total part of speech tag for that particular corpus. Use bigram concept and fill the entries in a table. This will provide the data for state transition probability. Now when we are solving the HMM problem, at that time we are using the Viterbi decoding algorithm. Viterbi decoding algorithm is based on the concept of dynamic programming. In dynamic programming, we always break down the large problem into small sub-problems. We calculate the solution for that small sub-problems, we store that solution, and we use that solution into next step. It saves the result for future purpose, therefore no need to compute the result again. Now in the next example, I will explain why we are going for Viterbi decoding algorithm. Now for example, the statement is assured to back the silver coin. For example, this statement is given, and we have to identify the part of speech tag for every word. Now for example, 6 words are there total. If assured word is there, so for assured word 3 types of part of speech tag can be possible, that is VBD, VBN and JJ. For 2 is only one, that is 2 is a part of speech tag. For back, again 4 part of speech tags are there. Then for the can be determiner, but sometimes the can be noun also. Silver act as sometimes noun, adjective and verb, and coin noun and verb. This is nothing but the total count of part of speech tag. Now we can see that except the 2 words, there is a ambiguity in every word. This assured, that is first word, contains the 3 part of speech tag, back contains the 4, then the word contains 2, silver contains 3 and coin contains 2. Now total number of ways are 3 into 1 into 4 into 2 into 3 into 2, so we require to multiply, so 144 possibilities are there. So it is not efficient if we try all this 144 possibility. only 6 words are there, and for that 6 word if we check only 144 possibilities, the solution will not be efficient. Now what we want, using Viterbi algorithm we are finding the efficient path, in which at every step we check the probability of that particular stage answer, and based on the probability answer we take the decision which part of tag to be selected, and based on that we are moving forward. So the efficient path gets selected using the Viterbi algorithm. So this is just explain, that is, for example, this first word assured, it has 3 part of speech tag, then 2, then this backward, then again silver and coin. So these all paths are very difficult because total 144 combinations are there, and to use all that 144 combination to determine the part of speech tag for 6 word is not an efficient approach. That's why we are using the Viterbi algorithm. Now we will solve the problem. We will start the problem from scratch, and here we start with the training corpus, and we can find out that at every path Viterbi algorithm will find out the efficient path rather than checking all that possibilities. Now these 4 statements are given. So this is the given corpus. S indicates the start of the statement and E indicate the end of the statement. Now these are the statement. Martin Justin can watch Will. Spot will watch Martin. Will Justin spot Martin. Martin will pat Spot. Now these are the 4 statements are there, and this is called as a given corpus. Now this S and E is nothing but start and end of the statements respectively. Now the first step is assign the correct part of speech tag to the training corpus. So this is our training corpus, and this is nothing but our training data, so it should be having a proper part of speech tag. So first task is to assign the correct part of speech tag so that we can test afterwards. Assign correct part of speech tag to the training corpus. Now this is nothing but the training corpus with correct part of tag, and for simplicity we are not going into the proper noun, then adjective, or for example this corpus contains only 3 part of speech tag, but here also we are not going into the detail, that is proper noun, we goes to the very coarse level. Now for example, Martin is a noun, Justin is a noun, can be modal verb, because here it is not act as a noun but it acts as a modal verb. Watch is verb. Will, here will is noun, then Spot will watch Martin, then now Spot is noun, then will is modal verb, watch is verb, Martin is noun. Will Justin spot Martin? Now here will work as a modal verb, Justin is a noun, Spot, now here it is noun but here it is Spot is nothing but spot, so it is acts as a verb there. Then Martin as a noun, then Martin noun, will as, again here it which acts as a modal verb, then pat as nothing but verb, and Spot as noun. Now we can see that in this corpus, based on their position, the part of speech tag of that particular word changes. So here a very coarse category is used, that is noun, modal verb and the verb. Now this is our first step, that whatever given corpus we require to assign the correct part of speech tag. Now next is creation of emission probability matrix. Now here what we require to do in emission probability matrix based on the Bayes rule. Now for just to check the data, because it is very difficult to continuous move back to the slide, so I have just pasted this data. So what you require to do when you create the emission probability matrix, at that time you are finding out the unique token from the corpus. Now Martin, Justin, Will, Spot, can, watch and pat, they are nothing but the unique tokens. Now what we require to do, we require to just make the apply the Bayes rule. Now probability of word given class is probability of class word divided by probability of class. Now this particular part of speech tag and word coming how many times divided by probability of that class. Now here classes are noun, modal verb and verb. Now total times noun is appearing, we just count that how many times noun appears, we keep that summation 9. Then for modal verb we keep that 4, and for verb we keep that 4. So simply from the training corpus, what we require to do, we require to count how many times n appears, how many times m appears and how many times v appears. After that we require to apply the Bayes rule. Now probability of class word, that is class and word, occurs simultaneously divided by probability of class. Now Martin occurs how many times? Now for example 1, then 2, 3 and 4. 4 by 9 we are getting. How many times Martin occur as M, that is modal verb? It will appear as 0 because it is a noun, so 0 by 4. Then Martin's appears as verb, it is 0 by 4 again. Now I will explain for the will, because will acts sometimes as modal verb and sometimes it acts as a noun. Now in this corpus will come as noun as 1 by 9 because only for this statement it acts as a noun. For example, Martin Justin can watch the will, but after that in second statement, third statement and fourth statement it acts as only modal verb, so it is nothing but 3 by 4. So modal verb probability is 3 by 4 and will as a noun as a 1 by 9. So you have to solve this problem, because by just seeing the value it is very difficult. So minimum one time you require to make the practice of this problem. So in this way we are completing the emission probability matrix and we are applying simply the base rule to calculate the emission probability matrix. Now our step 3 is creation of state transition probability matrix. Now here we are using the bigram model and we are using one word previous history. Now this is the formula for bigram. Probability of Wi given W of I minus 1. In this way also we can write down, this is nothing but the previous word and this is the current word. Count of Wi minus 1 Wi divided by count of W of I minus 1. For this simplicity I have put again the corpus here so that you can easily check the answer. Now here what we require to do, that this is nothing but the 3 part of speech tags are there, so the size will be 3 by 3, but we are adding this start of the statement and end of the statement. Now here how many times this is nothing but I minus 1 previous word. Now you require to check that after start of the statement how many times n appears. Now and divided by count of s, so 4 statements are there, so how many times after s n appears divided by count of s. So here the count of s is 4 because 4 statements are there, so denominator is 4, and after the start of the statement how many times n appear? This is the first, this is the second and this is the third, so 3 by 4. Now we require to check how many times after the start of the statements m appears. Now after the start of the statement only 1 times appears, divided by how many times s there? S is 4 times, so 1 by 4. How many times after the start of the statement v is there? No, that's why it is 0 by 4. How many times end up, because there is word, so start and end will not match. After that a noun and noun, so what we require to do, how many times in n corpus noun is noun is followed by noun, so and divided by how many times n appears. So we just require to count how many times n appears, so n 1 time. After that there is no combination and total number of n's are 9, so 1 by 9. Then how many times combination of nm appears? So nm appears 1 time, 2 times and 3 times, and 3 by 9 is equal to 1 by 3. So in this way we require to apply the bigram model to to fill the state transition probability matrix values. Now this is the simplest way. After creating of the emission probability and state transition, we can this is nothing but the training, that generation of the emission probability matrix and state transition probability matrix. Now for example the test data is given. Justin will spot the wheel. Now here wheel is a modal verb, but here wheel is a noun, and here spot is a verb and it is not a name. So we require to find out how many, that is we have to assign that part of speech tag for each word. This is the start of the statement and this is the end of the statement. Now we first check whether the ambiguity is there or not. For example, Justin is noun, but will can be noun, will can be modal verb, spot can be verb, spot can be noun, and will can be noun or will can be modal verb. So total 1 into 2 into 2 into 2, that is 8 possibilities are there. So if we want to find out the part of speech tag, and if we are not using the Viterbi algorithm, at that time we require to check that 8 possibilities to determine the part of speech tag for each word. But with Viterbi we are finding only the efficient path. Now we will start to do the solution, but when we calculate the solution, every time in front of your eye this table should be there, otherwise it is very difficult to solve the problem. And that's why here I have written the formula in detail, so you can check afterwards with your tables. Now the first word is coming as a Justin. Now see, Justin, when the word coming, we want to identify whether Justin belongs to which category. Now we have to identify. Here we are given by default Justin is a noun, so there is no ambiguity is there. Still we will calculate the probability. Now before Justin, start of the statement comes, so this is nothing but our Q1 state. Justin word is X2 and this is nothing but Q2 state, and here there is no ambiguity, so that's why we are writing the N. Now we require to just write down the formula, in which first is your base rule and second is your bigram. How many times Justin occurs as a noun, into noun, how many times after S noun is coming, because this is bigram, how many times noun is coming after the start of the statement. Now you require to check for this emission probability matrix and for this state transition matrix. So I am just directly picking the value, you can check afterwards. 2 by 9 into 3 by 4, we are getting the 1 by 6. So when we find out the part of speech tag for noun, as such there is no need, because by default after the morphological parsing we are already given that Justin is a proper noun. Still we calculate the probability, so Justin comes with the probability of 1 by 6. Now the next word is will. For example, Justin will. Now here the problem comes, because will belongs to the either noun or the modal verb. Now here we require to do for the two paths, will as a modal verb and will as a noun. Now previous is our noun, because Justin, this is the second word, that is will, of which we have to determine the part of speech tag. That can be M or that can be N, and the previous state is N with 1 by 6 probability. We are using the dynamic programming, so whatever the previous answer we are using in the multiplication, because in dynamic programming we solve the small sub problems and we store that answer and we using that answer in the subsequent states or subsequent calculation. So here after the first word we get the final answer, that probability is 1 by 6 and the part of speech tag is noun. We are not going to change, it is keep as a noun. Now here we require to do for the two times. First is for M and second is for N. Now this is the will state X2, Q2. We have to determine M, whether it is M or N. So we will try with both, and after that we require to write down the formula. So this formula is very much easy, that how many probability of will given M, and how many times after N M is coming, means after noun modal verb is coming. This is nothing but the bigram, so you just read like this, so it becomes very easy, that how many times after N the modal verb is coming. So from the emission probability and state transition I am just directly putting the value, which I am getting 1 by 4, but don't write only 1 by 4. We require to multiply with our previous answer. Previous answer is 1 by 6 and 1 by 24. Even don't multiply the values and get the answer in point, because it becomes very difficult. At last you can take the answer in a point. Now here the same procedure will follow, but instead of modal verb we are taking for the noun. So the probability of will given noun into probability of how noun, after noun how many times noun comes. So it is 1 by 9, 1 by 9, 1 by 81. Previous answer is 1 by 6, so we are getting 1 by 486. Now here the role of Viterbi plays. 1 by 24 and 1 by 486 is, there is no chance, because here the probability is very less, so we are not going by this path, so this path gets blocked, right? So there is no way to check all that 8 ways. Here the path gets blocked when will as a noun, because here the probability as will as a modal verb is very high, because 1 by 24 is greater than 1 by 486. So probability of modal verb is greater than probability of noun, therefore the result will be modal verb, and we are storing the 1 by 24 solution for the next step. So therefore here this is the will as noun and will as modal verb. Now this gets disambiguated, and here now will work as a modal verb, and with the answer of 1 by 24 we are proceeding. Now the next word is spot. See, the next word is spot. Here again the problem is there. But now here we disambiguated that will now is a modal verb, so we are going from M to V and M to N combination. Now see this, spot as a verb and spot as noun. The formulas are same as repeating, only we require to remember that previous answer is 1 by 24 that we want to store, and this state, that is Q1, is now our modal verb because we disambiguated for the will word. Now this is same, that is how many times spot, probability of spot given V, and how many times after the modal verb is coming, probability of spot given N, and how many times after modal verb noun is coming. So we are getting this answer, and this is very important to multiply the previous answer because the modal verb comes with the probability of 1 by 24. Now here we are getting 1 by 128 and 1 by 432. Now 1 by 128 and 1 by 432. Now 1 by 128 is greater than 1 by 432. So here the probability of verb is greater than the probability of noun. Here the probability of verb is greater than probability noun. So result spot as a verb, and it comes with the probability of 1 by 128. Now next word will be will. Now here again there is a problem because here will can be noun and will can be modal verb, but here we change that. Here our spot will part of speech tag is assigned as verb and not the noun. So we are going by this way, that is N to M, then M to V, and here we are now checking this path. Now our paths gets reduced. Now for the last word we are repeating the same procedure, that this formula is same. And here I just want to say the important thing, that here there is no as such standard formula of smoothing. You can use a Laplace smoothing also, but here also even you don't go for Laplace smoothing, even you apply the simple formula in a simple way in which your answer should not be 0, because for example here I am using 1 by 1000. Why? Because the probability of will given M is 3 by 4, but probability of after verb modal verb is 0. So when we use a 0, what will happen? The entire answer gets 0. And here there is no problem in this problem, but sometimes it may happen that from the statement that probability is more, but because of one chance or one pair is not present, at that time the answer becomes 0. So that cannot be, or that should not be happen. So therefore here the probability of verb after M is coming is 0, but it is replaced by 1 by 1000. So 1 by 1000 is a very small number, so the care is that answer should not be 0. And here previous answer is coming with 1 by 28, and 1 by 28 is multiplied, and we are getting a very large number. Denominator means this number is small. Now we will check for that noun, and we are getting 1152. Now here just previous data is copied, so you can easily make that. This is the small rectification, that we are comparing 1 divided by 512,000 to 1 divided by 1152, and 1152 is, this number is greater than this number, so this number is nothing but noun. So result will as noun. Only this part you have to understand, we are comparing this value and this value. So now result will be will as noun. So in this way we go by this way, noun, then we go modal verb, then we go verb, and then again we go to noun. So in this way we are following the path using the Viterbi algorithm. Probability of will as noun is more, that is nothing but our last, and result of the pause tagging after applying the HMM model. So this is the result. Justin will gets noun, will gets modal verb, spot gives verb, and will gets the N. So this is all about the Viterbi pause tagging problem. These are the references for this HMM model and the derivation. Thank you. And in the next video my planning is to take some more problems on Viterbi algorithm, because in exam sometimes state transition matrix and the emission matrix is given, and sometimes they just represent by diagram, or sometimes they given just a raw corpus. So you should be able to solve the problem in any situation. Thank you.